Friends, today let us take up a few MCQs on the topic kinetics. Now, just to give a brief introduction, the rate of reaction has been designated as some 1 upon nu j dj by dt, where J is the concentration of the reactant or the product, and dt is obviously the change in time. So basically it is change in concentration of either the reactant or the product upon the change in time. And nu j, as we have shown, 1 upon nu j is the stoichiometric coefficient. Now supposing there is a reaction A going to B, then the stoichiometric coefficients for both reactant and the product is 1. But supposing the reaction is 2A going to B, then the stoichiometric coefficient for A, which is the reactant, is 2, and the stoichiometric coefficient for the product B is 1. Now there's one more small point, that if you have the disappearance of a reactant, then there is a negative sign which is associated with the rate, as we have shown over here. So if supposing this J is the concentration of the reactant, then we'll put a minus sign over here just to show that the concentration is decreasing as the time goes on. Whereas if J were the concentration of the product, then as the time goes on, the product concentration increases, and therefore there will be a positive sign. So disappearance, there will be a negative sign; appearance, there will be a positive sign. Now with this brief introduction, let's take up the first question. The first question simply says that there is a reaction half A going to 2B. So the stoichiometric coefficient for A is half, and the stoichiometric coefficient for B is 2. And what it is asking? It is asking that what is the relationship between the rate of disappearance of A and the rate of appearance of B. That means the rate of disappearance of the reactant and the rate of appearance of the product. So this is what he wants to ask, and he has given 4 choices over here: A, B, C, D, and as you can see, there are various coefficients that are associated. In this particular choice, there is no coefficient which is associated, so it appears that this may be a doubtful choice. So we can in fact not concentrate first on this, but concentrate on the choices A, B, and D. Now, rate of consumption of A, that means the rate of consumption of the reactant, will be simply by this formula minus 1 upon half, because remember, half is the stoichiometric coefficient. dA by dt, that means where A is the concentration of the reactant, is equal to half of dB by dt. Now remember, this half is still coming over here because the stoichiometric coefficient for B is 2. So this is 1 upon 2. Stoichiometric coefficient is half, so it is 1 upon half. And this is the B is the concentration of the product. Now if you simply simplify this, this will become minus 2A dA by dt, and this will become half dB by dt. And from here, dA by dt will be 1 upon 4 dB by dt, which is our choice over here. That is, our B choice is the correct one, and the rest of the choices, A, which is half, and D, which is 4 times, is not correct. And hence, very simply, we can find out the relationship between the rate of the reactant and its relation to the rate of the formation of the product. Now in the next question, we have a reaction going as follows. 2A, that means 2 moles of the reactant are reacting with B, and they are producing 1 mole each of C and D. So there are two reactants and there's a formation of two products. And for this particular reaction, there was a kinetic data which was taken for three different sets. Three different sets means that the concentration of A and B, which were the reactants, was altered and the rate was measured. So in one set you had one type of concentration of A and B, another different concentration, and third different concentration. It has been shown in this table over here. You can see initial concentration of A is 0.1 molar, B is 0.1 molar, rate has been found to be 1.2 into 10 to the power minus 3. Now in the second set, you have kept the concentration of A as constant 0.1, but you have doubled the concentration of B. So this you have doubled, but the rate has still remained what it was over here. This is one observation. The second observation is that in the third set over here, you have doubled the concentration of A, but you have kept the concentration of B the same as in the first set, and you find that the rate has been doubled. Now this is what we have the data, and how do we interpret it? The interpretation is simple enough. If you increase the concentration of B, and if the rate does not change, that means the rate remains the same. You have doubled the concentration of B, but the rate remains the same. This clearly shows that the rate of reaction is not dependent upon the concentration of B. If it is not dependent upon the concentration of B. On the other hand, if you double the concentration of A, you find that the rate is also doubled. This clearly shows that the rate of reaction is dependent on the concentration of A. Now, this means that we have the following four choices. You can easily eliminate those choices where you have a dependence on B. That means you can eliminate this, you can eliminate this, you can eliminate this, and finally you have only one choice left, which is that the rate of formation of C is some K, which is the reaction constant into the concentration of A. So this is our clear choice in this particular example. Now, hypothetically, if supposing we say that the rate of formation of C was dependent upon A, but it was dependent upon the square of A, which means that if you had written this as K into A, and if supposing you doubled the concentration of A and you made it 2A, then the rate would become 4 times. So obviously this is not we find. That means if you double the concentration over here, from here to here, you only double the rate. You don't make the rate go 4 times. This means that this hypothetical choice is also not correct, and we are left with only this choice D, and that is the right answer. Now let's just rub this out and look at a slightly different type of a question. And here we try to introduce a top point, which is, let us say, called the T half. Now T half is basically the time taken by a reaction to be complete halfway through. That means what we are saying is that supposing you have a reaction A going to some products. So you have a reaction, let us say, let us put this line over here. Let us say our third question is that some A is going to some products. And if the A is going to some products, we need to know these certain important aspects. We want to have an idea of what will be the concentration of A at a particular time T. And in this matter, we introduce what is called T half. So we say that T half is equal to the time taken by the reaction A going to P when it is half complete. That means the concentration of A has become half. Now in this particular question, T half has been already provided to us. It is 1 hour. So this is 1.0 hour. And we have been given the concentration of initial concentration of A. The initial concentration of A is 2.0 moles per liter. So these are the two important pieces of information. We have T half value, we have the initial concentration of A, and then it says that this reaction is actually a zero order reaction. Now what do we mean by a zero order reaction? A zero order reaction is a reaction in which the rate is not dependent upon the concentration of the reactant. So we can therefore write a rate equation for a zero order reaction in the following manner, that sum minus dA upon dt should be equal to some K, which is basically a constant. Now if you integrate this equation by simply modifying it, you can simply say that you want to integrate this equation between the limits, let's say a0 and a, and you have d of a and is equal to some k of dt, and this will therefore result in basically minus of a minus a0 is equal to some k0 t, and this could be then written as a0 minus a upon t is equal to k0. Now why we need to write this equation is because as a first step in this question, the question is asking basically the following. Let's just repeat it or write it down. The question is asking, let's say, how much time is required for the concentration to change from 0.5 molar to 0.25 molar. So he wants us to evaluate the time for this zero order reaction for a specific concentration change, that is from 0.5 molar to 0.25 molar. Of course, we know that the initial concentration of A is already 2.0 moles per liter. So for this, we first need to calculate our rate constant. So if we know the rate constant, then we can use this particular rate constant to evaluate the time t. Now we have already we can use our t half over here. So if you put your t half over here and the values of a0 and a, remember that t half, if that means k0 is equal to a0 is basically 2 moles per liter minus a is nothing but when the concentration of the reactant has become half, because at time t half the concentration is half, so this is nothing but 2 by 2 or a0 by 2, and this upon t half T half is 1.0. So this is basically, you can figure out that this will become basically 1.0. So your rate constant has been evaluated as 1.0, and of course there will be units to it, because this is in moles per liter and this is in hours. So this will be some moles per liter per hour. Now once we have this value of our K0, we can use this K0 value to figure out how much time will be required for the concentration to change from 0.5 to 0.25, provided it's a zero order reaction and these are the concentration factor and other things are already given to you. So for that means here we need to find out T. So T will be nothing but some A0 minus A upon K0, and A0 is 0.5. That is the starting concentration, and that is the concentration of the reactant after time t. So this is A is 0.25. So that means this is some 0.5 minus 0.25 by K naught. K naught is 1. So this is 0.25. So the time that it will take for the concentration to change from 0.5 molar to 0.25 molar is basically 0.25 hour, because remember that this is this unit will be hour inverse. K0 is in hour inverse, so this will become in hours. Now obviously you have figured it out. The choices have been also given in hours. So the choices that were given was, let's say A was 4 hour, B was 0.5 hours, C was 0.25 hour, and D was 1 hour. Now we know, obviously we have calculated that the C choice is correct, that is the time taken is 0.25 hours. So this actually gives you a simple handle on, that is to, if you know the T half of a reaction, you can then find out from that the rate constant, and once you know the rate constant, then that rate constant can be used to figure out the time for any change in concentration at time t. Let's take up another example of a similar type, and in this particular case, let's just rub this out once again. So let's rub this out over here. And in this particular case, we again use the idea of T half, and besides the idea of T half, in the earlier case we had what is called a zero order reaction. That means we took the example of a zero order reaction. You can now take up the example of a first order reaction. So we have a reaction in which T half is given and the order of the reaction has been given, which is first order. So let us see what it is asking us and what is the question. So let's say our fourth question says that T half has been given. T half is equal to 6.93 minutes. T half has been provided to us, and what it is asking, calculate the time which will be required for the reaction to complete to 99%. So calculate the time required for 99% completion of reaction provided it's a first order reaction. This is what we need to figure. And here let's just write down the four choices that have been given. This is A is 230.3 minutes, B is 23.03, C is 46.06, and D is 460.6. These are our four choices that have been provided to us. Now again we have to follow the same procedure. In the first step we need to first calculate our K, which is the rate constant, and then by using that K we have to figure out the time required for 99% complete. These are our two steps. Now to be able to calculate K, we need to write down the rate equation for the first order reaction. Here this is simply sum minus dA by dt is equal to sum K into A. This can be transformed as sum minus of dA by A is equal to sum K into dt, and we can integrate this equation between the limits a0 and a. And once we integrate this equation, we remember from our simple mathematics that an integral of dx by x is ln x, and so if you have this already formulated, this is of the same form, dx by x, dA by a, so this will be simply minus integral of ln a minus ln a naught is equal to sum kt, and from here this is nothing but ln a naught by a is equal to kt, and k from here is now ln. This log natural can be sort of converted into to the base 10 by multiplying by 2.303. So this will be some 2.303 into log a0 by a upon time t, and so in fact we need to find out the time t. So it should be, we have to first of all find k. So let's figure out this k first of all. So log a naught by a, we have to figure this out at we have been given t half. So at t half, if you put in the value, this can be easily evaluated, because this will become some log of a0 by a0 by 2, so it will become basically log 2. So this will be simply written as k is equal to 2.303 into log of 2 upon t. T is from here 6.93, and log 2 value is 0.301. So when you put in this value, you find that this will turn out to be finally 0.693 by 6.93 equal to 0.1. So you have evaluated as a first step the rate constant of this first order reaction given the t half value, and at t half we know that the the initial concentration will become half. So this will be A0 by A0 by 2, it will be log 2, and so simply K is 0.1. Now once we know this K, we can now put this K, find out the time required. Now 99% means that if supposing you started with 100%, that means if A was 100%, you have completed 99%, that means only 1% is remaining. So using the same equation, we can figure this out also. So let's say we can say that our T will be some 2.303 into log of 100 by 100 minus 99 upon K. K is 0.1. Now this will be nothing but log of 100 by 1, which is 10 to the power 2, so it will be 2 log, so root 2 log 10 to the base 10, so this will be 2, so it will be, this will be basically equal to 4.606 divided by 0.1, and so this is nothing but 46.06 minutes. So this is how you can figure out the time required for a first order reaction to go to 99% completion. There are two steps. He has provided us the T half. From T half we calculate our rate constant. Using that rate constant we can calculate the time required for 99% conversion, which is 46.6. So naturally our choice C is correct. Rest of the choices D, B and A are not correct. Friends, let us stop at this point and we shall take up some more MCQs on kinetics at our later lecture.